Hubhopper Originals.
To start your podcast for free, log on to studio.hubhopper.com.
Hello everyone and welcome back to Indian Genes. As promised, we continue with this special season on space exploration, and we did speak about getting legends on the show. Our guest today is just one such legend. She is an American astronomer, best known for her work on search for extraterrestrial intelligence, SETI. She's also the former director of the Center for SETI Research, holding the Bernard M. Oliver Chair for SETI at the SETI Institute. In 2002, Discover magazine recognized her as one of the 50 most important women in science. She earned a Bachelor of Engineering Physics degree as an undergraduate at Cornell University and as the only woman in the engineering program. Her professional interest in astronomy emerged as she pursued a master's degree and PhD at the University of California at Berkeley. It was her PhD thesis which coined the term brown dwarf while researching small mass objects that failed to stably fuse hydrogen. She was the project scientist for NASA's High Resolution Microwave Survey, the HRMS, in 1992 and 93, and subsequently director of Project Phoenix under the SETI Institute. Her astronomical work is well illustrated in the Carl Sagan's novel Contact, and in the film version of Contact, the protagonist, Ellie Arroway, is played by Jodie Foster. Tarter conversed with the actress a few months before the filming, and Arroway was largely based on her character. So ladies and gentlemen, this particular podcast episode is a very special one, and as you can see from what I've just been saying, when it comes down to what our guest today has been involved in, has pioneered, and has been doing over these years, I'm sure this is something you do not want to miss. We now proudly present a very interesting conversation with a legend, none other than Jill Tarter. Hi Jill, and from one earthling in India to another in the United States, a big welcome to you from Indian Genes.
Well, it's a pleasure to be with you.
And I think a lot of my listeners are going to be absolutely tuned into everything you're going to be saying to them. The topic that we're going to be covering today is, for some reason, has been in the news all of a sudden. And have you found that as well, Jill, happening where you work?
Well, it seems that on a cycle of like 3 or 4 years, people will get interested again, people will make claims, and media will pick it up, and then it feeds on itself for a while.
I also think maybe it's because of there have been certain happenings, or we may say observations or discoveries that have happened recently. And I think one of that would you call it the Uma, and that got in a lot of attention. Do you think that started it a little bit in this cycle at least?
Yes, I think Oumuamua was a big piece of this. I mean, those of us who were huge science fiction fans remember Arthur Clarke's novel, and it seemed an obvious comparison to make. And
before we get further, Jill, if we could ask you, or the young listeners who are listening to us at the moment would want to know, when did this journey start for you, Jill? Because I think you started off with an interest in engineering, and how did looking out into space and looking for extraterrestrial life, how did this get your fascination?
Well, you're right. I did my undergraduate degree in engineering physics. And as a result, I got very good at solving problems. But I did not enjoy the educational environment in the engineering school at Cornell when I was there. I was the only woman in a class of 300. And when I finished, I said to myself, well, if engineers in general are as boring as my professors, I'm going to go looking for some more interesting problems to solve. And that led me to taking a lot of different classes at Cornell for a year, and one of them was a class taught by Ed Saltpeter about star formation. And I really thought, wow, who knew that stars had a whole life cycle dependent mainly on their mass? And I said, gee, these are really interesting problems, so I'm going to switch to astrophysics. And I did, and went to graduate school at Berkeley. My first year there at Berkeley, I was supported as a research associate program, the first desktop computer that we ever had, a PDP-8/S. Now, it took two people to get the computer up on your desk, right? That was that big, but it was a marvel, and it had no language. You had to program it all in Optical. You had to set the ones and zeros for the 11 instructions that this computer could do. And I learned that skill, and many, many years later, while I was still a graduate student, that piece of equipment became surplus and was given to an X-ray astronomer by the name of Stu Boyer, who had a very clever idea about using UC Berkeley's radio telescope at Hat Creek and piggybacking a SETI search on the radio astronomy observations. But of course, he had no money to do this, and so he went begging, and somebody gave him this old computer as a surplus piece of gear, and he arrived at my door and handed me something called the Cyclops report, which was an engineering design study that had been done a couple of years before at NASA Ames. And he said, here, why don't you join my group? And I read this Cyclops report, and I was just blown away. I was so excited by the fact that I had the right set of skills, and I was in the right place at the right time to try and do a systematic scientific exploration to try and answer this old question that humans have asked forever. Are we alone? And so I got hooked, and I've stayed hooked ever since. So it was an accident that I got into SETI, and it was all because I knew how to program very strange early computer.
Yeah, and I think the Cyclops, the project was quite interesting as well, or what it was intended to do, because I think the intention there was to coordinate that a large number of radio telescopes to search for Earth-like radio signals, and mainly I think you all were looking at distances of about 1,000 light years, right, at that time, to find intelligent life?
Oh, that's where there are about 1 million stars within that distance, and they thought that would be a good number to search. But the Cyclops report was again, an engineering design study with no cost boundaries. So they dreamed up this array of 1,600 100-meter radio dishes that they were going to use and add the signals together. I mean, we didn't actually even know how to do interferometry at the time. Mm-hmm. So they weren't even using those, if you could ever have built them, those 1,600 radio dishes were just, the outputs were just summed.
And I think at that time, was it, the choice was radio and optical, or optical came in later?
Optical had been suggested around the same time by Charles Townes, but we actually didn't have the technology to implement it. So optical came in about 30 years after we started the radio, when we finally had appropriate computers and detectors.
And while you were doing this or looking for these signals, especially because it was you're going to go out into space, does the dust matter? Because if there's no dust rather in space, is it better that way?
Well, dust is a problem for the optical because the size of the dust grains are about equal to the wavelengths of the radiation and optical frequencies. And so dust heavily scatters and absorbs the optical signals. But radio wavelengths are so long compared to the size of the dust grain that they don't see the dust. And so you can look completely through the galaxy to see the center of the Milky Way galaxy in the radio, which we've never seen in optical. Optical distances are, in fact, looking for signals. The distance is limited by the dust. And then as you go into the infrared and the radio, you have less scattering and obscuration.
And I think you also, I would like our listeners to know that you were the one that actually came up with the name brown dwarf. Not only the name, but you actually researched and got into that. But that's a great name. It is taken for granted now, but that must have been an interesting story. And how did it happen at that time? Because I think, for a brown dwarf, any gas planet, it had to be at least 13 to 80 or 70 times that of Jupiter, right?
Right. When I was a graduate student looking for a thesis topic, we were beginning to talk about this idea of missing mass in the Milky Way galaxy. We thought that there should be about 10% more mass in the galaxy to explain the motions of distant stars in the galaxy than we could add up when we counted the mass of all the stars and the dusts and the gas that we knew about. And so I wondered if indeed stars that were born in large molecular clouds and collapsed, but indeed the mass of the gas cloud that collapsed was too small to get hot enough to actually stably fuse hydrogen to helium at their centers. I wondered if these tiny stars that would eventually become dim, they would never, they just didn't turn on, whether that could be the missing mass. And so I had to try and figure out what these stars would be like, had to do code. I actually used codes from Livermore, from the bomb makers, to do stellar interior. And then I tried to fit an atmosphere around this small star. And at the time, our knowledge of opacities at low temperatures and low densities were really poor. And I could never get a good numerical solution that would allow me to fit a proper atmosphere around my stellar core and thereby decide what color they would be, where the light could get out, what wavelengths. And at the time, I was aware of a statement by Edmund Land, who was running Polaroid company. And Land said, brown is not a color. So I couldn't get a good color temperature. I called them brown because I didn't want to mislead anybody by saying they were red or something else. So brown is not a color. I couldn't get a good color temperature, so I just called them brown dwarfs, and it stuck.
Wow, that's such an interesting story. And when you were thinking of this, like you said, you were a student at that time, and we normally look at these discoveries or inventions and we think of you or what you all are doing. Would you think about it mathematically, or are you thinking theoretically first, or trying to put this together, or you're doing both of it together? How does this?
For me, it was doing both together. It was thinking about the question and trying to figure out what kind of calculations I could make and learning the math that I needed to know in order to do those calculations. And it was all a piece of the same exploration.
And getting to the interesting part of SETI and all the search for extraterrestrials, would you like to tell us how that started for you and your involvement there in the early days?
Well, the involvement was by accident because I knew how to program this PDP-8S computer. And we built, so University of California at Berkeley had a radio telescope in Northern California. And Stu Boyer had this interesting idea about you could take the radio signal, the voltage is a function of time coming out of the telescope, and you can make a copy of that signal. Basically, you can noiselessly copy radio signals because you're measuring both the amplitude and the phase from the telescope. And then you could analyze the copy that you'd made for signals that were engineered rather than astrophysical. And basically that meant that you would look at the signal with much higher frequency resolution. You would break that radio data up into a very large number of individual channels. And then you'd look for a signal that was compressed in frequency. It only showed up at one of those channels, although over time it might change. The channel that you found the signal in might change with time because of the rotation of the Earth and a Doppler shift that caused in a narrow signal. So we did that. We built a spectrometer we built a 100-channel receiver, and then those channels were only 1 hertz wide. Astronomers were typically looking for signals, even if they were looking for atomic or molecular lines, they were still looking for signals that were thousands of hertz wide. And so we narrowed down to these 1 hertz channels and went looking wherever on the sky the radio astronomers were looking and at whatever frequency they were looking. And we were looking for these engineered signals. And of course, we found them. But we quickly learned that the hardest part of this search was going to be discriminating between signals that were actually coming from the sky and signals that we were generating ourselves in satellites or on Earth, radio interference. And that remains the case today as we get more and more uses for the radio spectrum. We get noisier, and so this relatively clear window on the universe that we used to have is now closing, and we have to pay more attention, use more computing resources to distinguish between this interference and the thing that we're looking for.
And was this something that also led to the HabCat, or us coming up, or you coming up with a catalog of habitable systems or habitable planets? And that's when it started. People know about it today, but how did you define it then, or did you set out to see what would the conditions have to be for a habitable planet?
Yes. When we decided after a decade of renting time on large telescopes around the planet so that we were on the air maybe 15% of the time, we finally decided that we wanted to build our own telescope so that we could be on the air all the time. And one of the motivations for doing that was to be able to find transient signals, signals that only showed up once, are very hard to get validation for. So we wanted to build our own telescope to do this. And then we said, okay, now we're not piggybacking on anybody else's observations. We have to decide where we want to point that telescope. And first thought is, well, we know one place where there is life and technology on a planet around a particular type star. And so we should probably look at catalogs of stars to find other stars that are like our own sun. Since we knew it happened once around such a star, those stars would be preferred. And so we went through the available stellar catalogs. This was long before Gaia, and picked stars that were as close to our sun as possible in terms of spectral type, in terms of age. And at that time we were not very keen on binary systems. We didn't know whether planets could stably orbit binary stars. So we excluded those. We wanted stars to be, and so we built this habitat. And we built it before we ever knew that there were planets around any kind of stars. And now, because of the Kepler spacecraft mission and because of tests that follow on to that, we now know that there are more planets than stars. Every star, on average, has at least one planet. And so we could therefore relax our criteria and say, well, to have planets, maybe a star doesn't have to be like ours. And we began to put more emphasis on nearer stars, stars that were closer to us, because we could detect the faintest signals. And so now our catalogs have two components. They have stars that are like the sun, and they have stars that are close to us.
Right. And I think the Allen telescope array was what you were referring to earlier when you said you decided to have your own, you decided to have your own systems looking out into the sky. And was that the system that you were talking about?
That's correct. The Allen telescope array was built at the Hat Creek Observatory in Northern California. And we had hoped to build 350 small telescopes. So it's the first time that we built, it was the first time we built a large, effective telescope by building a large number of small dishes. So we had hoped to build 350 6-meter dishes. It turned out that there was a lot more research and development that we needed to do in order to figure out how to do such a thing. And so we ran out of money. We didn't get to 350, so we have 42 telescopes.
Okay. And you mentioned earlier, interestingly, just thinking about it, where you said that where you were thinking about the brown dwarf, you were doing your math at the same time. Connected to what you're doing at SETI, or what SETI is doing, or what everyone is doing now when we're looking for extraterrestrial life, is it a fact that math is a universal language, or is it that we as humans look at abstract math or some kind of symbology that we can represent, but does that also limit it? It could be the way we express ourselves through math, and there could be different explanations or different formulas, but does it mean that everybody all over the universe is doing the same thing if we have to find somebody or a signal?
Well, I'm inclined to believe that everybody is counting some way or another. But this question of math, at least math as we understand it, being a universal language, I think is less and less robust. Because we're now understanding that the way that we express mathematics is indeed ruled or shaped by the structure of our brain. And that somewhere else, some other creature with a totally different brain structure may be expressing the same concepts, but in a way that is so foreign to us that we don't identify it as the same thing. So that used to be one of my givens, right? I used to say confidently that math will be the universal language. And now I'm not so sure.
And interestingly, you were mentioning about looking for these signals early on, and I just want to understand that a little bit more when you said look, and you said you used the word you were looking for deliberate signals because we're trying to look for intelligent life. Let's stay with intelligence life for the moment. So then are you looking for some patterns in those signals, or are you looking for something that does not form a pattern, or something has to be weird in that form?
Well, I think I used the term that we're looking for engineered signals.
Correct.
So we're looking for something that, as far as we know, we can produce with our technology, but nature can't produce. So in the radio, that turns out to mean frequency compression.
Hmm.
So we can look at the radio sky and see what is the narrowest emission structure that we can see from natural sources. That turns out to be saturated masers. But the energy from these masers is still spread over a frequency range of something in excess of 300 hertz.
Mm.
But with our technology, we can produce signals in the lab that are much narrower than 1 hertz. Now, as the radio signal travels through the interstellar medium, a signal that's just a pure tone at one frequency will in fact get dispersed, right? And it will get broadened. And so realistically, we've kind of said practically we should be looking for signals that are on the order of 1 hertz or a little broader, but less broad than the 300 megahertz that we would get in terms of a maser signal. So that's kind of sandbox frequency compression that we've set up in the radio. And when we do the same kind of argument in the optical, turns out it's time compression that distinguishes an engineered signal from an astrophysical signal. So we're looking for bright pulses of light that last for a nanosecond, a microsecond, a millisecond, not longer, because nature can make pulses that are longer. So time compression and frequency compression have been the things that we have decided distinguish an engineered signal from an astrophysical signal. And so we look for patterns in frequency and time that are indicative of these kinds of signals. But now that we have the ability to build neural networks and use machine learning, we've been able, instead of saying to the computer, tell me whether there's this particular pattern within the data. Now we can say, look, here's noise, that's what noise looks like, and here's data. And is there anything in the data that doesn't look like noise? So we're just beginning a new era of being able to say to the computer, look at these data and tell me if there's any kind of pattern here that is not noise-like.
And should you find that whenever you do, and I'm sure these keep happening, then we have to take into account the distance that it is traveling as well. Because if you're looking for some kind of a signal and the distances that we're talking, or the light years that we're talking, so we would always, in every case, be finding out about the past. It would be difficult to know that. So any signal that we do get would have happened quite some time ago, right?
Yes, if it's coming from our galaxy, it could be tens of thousands up to 100,000 years in getting from the origin, the transmitter, to our receiver. And that's why Philip Morrison, who was one of the early pioneers in this field, used to refer to SETI as the archaeology of our future. Mm-hmm. So it's, if there's any information content in the signal, we will be learning about their past because of the finite speed of light. But if we successfully detect a signal, we're going to learn that it's possible for us to have a long future, because the only way that two technologies can be close enough in space and overlapping in time is if on average the technologies persist for very long times, long in cosmic terms, not just human terms. So on average, if we succeed, on average, we're going to learn that technologies have long lifetimes, and therefore we can look forward to a long future. I mean, it doesn't mean that we won't screw it up,
Yeah.
screw ourselves in.
Also, if that is the time that we're talking about and technologies have moved on, the possibility of us actually interacting or finding any alien race, they would have themselves moved forward in AI as well. So the way we are sending probes currently to our planets or our neighboring planets, they probably could be doing the same thing. And so we may not first of all get directly in touch with them, but may just encounter their probes. That is AI.
Yes, that could well be. I think that statistically we can say that any other technology that we discover, however we do it, is going to be older than we are. And therefore, I presume we'll have more advanced technology. They can't be any younger, because if they didn't have a technological capability that was at least comparable to ours, we wouldn't find them. They would be invisible. And if they're older, then there's potentially a lot we could learn.
And when you are looking for currently life, and we want to just try to understand exactly, because that's the core of what SETI is doing, and I'm sure it's been your passion all your life. When you talk about intelligent life, and when you talk about, let's say, microbial life, how do you look at both these differently, and finding any one of them, do you think is going to be different or have a different impact for us? For example, tomorrow if we find microbes on Mars, we detected methane some time ago. It didn't create such a big stir because it still seemed to be okay. But if we do encounter another being that is intelligent, then that's a different ballgame altogether, right?
On the other hand, a couple of months ago, there was a discovery of phosphine gas in the atmosphere of Venus. And people got really excited because given how much we thought had to be there to produce the signal that was found, and we went through all kinds of chemical matrices, we couldn't figure out a way to make that much phosphine without biology being part of it. And so people got really excited about this potential ambiguous, yes, detection of perhaps biology in the clouds of Venus, and people were very excited about it. But I think the disconnect or the discontinuity is because the thing that we like to think about most as humans is humans, right? And so we've been wondering whether there's the other, right? Since we walked out of the caves and started looking up at the sky. This is an old question. And we're really interested in calibrating our place in the cosmos. How do we fit in? Are we common? Are we unique? Are we the lowest technology on the totem pole, or are we more towards the habitable end? It takes a cosmos to make a human, but where do we fit in on some scale of intelligent creatures in the cosmos? So I think it's a bias that comes from our own selfish interest.
Evolution could have happened in different ways, right? And when it comes to intelligence, I think intelligence is a byproduct of evolution itself. And if it happened in so many ways right here on Earth, just thinking of the ways it could happen all over different planets or different other worlds.
Well, yes. The question is, can evolution from chemistry to biology to technology happen in different ways. We actually don't know the answer to that. Because what we're looking at on Earth is a biological evolution that all seems to go back to the one last common ancestor. Biology's really only happened in one way. We don't know if it can happen some other way. As a physicist, we like to talk about branching ratios. If an experiment can have multiple different kinds of outcomes, we'd like to know what percentage of the time you get outcome A, what percentage of time you get outcome B, etc. We don't know that yet about life and biology. And we don't know the difference between what was absolutely necessary and what is contingent. I often like to tell students that if we had prehensile tails, like monkeys, we would have some just so story about why tails are required to have intelligence. And without another example of biology, I often said that we will never understand what is necessary versus what is contingent in the way that biology happened on this planet. But actually now there's a whole new science of synthetic biology. And we're beginning to build from very simple molecular components. We're beginning to be able to build more and more complex structure. So perhaps this new study of synthetic biology will in fact give us a way of understanding what is necessary versus what just happened as contingency. So I think that's an exciting new trend. It's kind of like when we were talking about what technologies we could detect, and we can only detect the technologies that we so far know about. I'm looking for radio waves and optical waves and infrared waves, but maybe the thing I should be looking for are zeta rays. I don't know what a zeta ray is. It's a technology we haven't invented yet, so I don't know how to use it in a search. And the synthetic biology may, in fact, tell us that there are ways to move from chemistry to something that we would recognize as living that isn't the DNA, RNA-based biological chemistry that all life shares on this planet.
We've also found, or we keep finding, strange life on our old planet. And we should not forget that, because there are certain places on Earth that we've not yet detected, or we find it too harsh. So I think both of those things seem to work together. As we keep discovering exoplanets, or strange exoplanets, we keep discovering strange places or strange forms of life, right? So it seems to be telling us that there is life or a possibility.
Yes. So exoplanets and extremophiles have been the huge game changers over my career. And now we know that there is a great deal of potentially habitable real estate out there. And the scientific exploration in this century is going to be trying to figure out whether any of that is actually inhabited.
That's going to be interesting, because bacteria seems to be the dominant life form on Earth, right?
Absolutely. Absolutely. And so we talk about looking for biosignatures and looking for technosignatures. And the biosignatures may be more ambiguous than the technosignatures, because we look and we think about what does life in the aggregate, how does it modify its environment? And we look at the disequilibrium chemistry of the atmosphere of Earth. So the coexistence of methane and oxygen, which are very reactive gases If you put them together in the laboratory, you get water and carbon dioxide. And of course, that's happening in the atmosphere all the time. But because we have biology on the surface of the planet, you have this huge source function that's replenishing these gases. You have photosynthesis producing oxygen and bovine flatulence producing methane. But there are other ways of producing oxygen, other ways of producing methane that are abiotic, don't require life. And so this disequilibrium chemical signal may not be unambiguous. You may have questions about whether you found life. With respect to the technosignatures, the things that we're thinking about, from signals to building large megastructures in space, those are likely to be completely unambiguous. But they're all part of the same spectrum. They all fit under the same umbrella of astrobiology, looking for life beyond Earth.
Would those large structures that you're talking about that we could be looking for or find, would a Dyson sphere be one of them?
Dyson sphere would certainly be one such structure, yes. The other thing that I like to think about as another example is think about this wonderful system called TRAPPIST-1. Right? It's 7 roughly Earth-sized planets orbiting a tiny little red dwarf star. And each of those planets is at a different distance from its star. So naturally, they should be at different temperatures. But when, in the next decade or two, we build telescopes that are large enough to actually image these individual planets in the TRAPPIST system, what if it turns out that they all are the same temperature? They all look the same. Right? That is not going to happen naturally. That's going to require some engineering, some planetary scale engineering. But it would, in fact, be another unambiguous technosignature.
And that would be something like a Civilization 3 that could have that ability or more, right?
It would certainly be a technology that's far in advance of ours.
And I guess we've also heard that you've recommended that SETI changes its name from search for extraterrestrials to search for technosignatures. Is that true?
Yes. And the reason is that I think it makes it makes the obvious parallel to the search for biosignatures that astrobiology seems very willing to undertake and fund. And by making this parallel and making the point that this is just another way of finding life beyond Earth, I'm hoping that it doesn't have the same funding problems that we have had historically with SETI and laughing at little green men searches.
Yeah, but we want to hear about that as well. And what do you think about it? Because everyone knows the stories, everyone's seen the movies, we know what's happening in pop culture, the XFiles, and we've grown up on the XFiles actually. So kind of my favorite. But do you see that ever happening, a contact?
I don't know the answer to that. That's what we're trying to figure out. Is there any life and technological life beyond Earth? So if the answer is yes, then perhaps contact is feasible. If the answer is no, then no. But we don't know the answer to the fundamental question.
Yeah, and what about the wow signal, Jill? That was interesting as well when it happened. And was it significant, or was it, or could it have been a signal, or like we were talking about patterns earlier? And did that fit your bill of the exact light or the sudden blob, the wow signal?
I often say that if I had been in charge of that search, you would never have heard about the wow signal. because the team had a scheme of a way of trying to discriminate between signals coming from the sky and signals being produced by our own technology. And they had two receivers, and they required that a signal would first be seen in the east receiver, fade away, and then come up in the west receiver and fade away. The WOW signal was seen in only one of the receivers, and they actually don't know which it was, east or west. And therefore, to me, it failed the validation, the confirmation test. And I would have said, no, I know it's very strong, stronger than anything you've seen, but it failed the test. And I think that credibility and verification is key to the whole SETI project. So for many reasons, but validity being one of them, we've developed something that we call the Rio scale. And hardly anybody knows about it, but if you think about earthquakes and you think about the Richter scale, you know that a magnitude 7 earthquake is a whole lot stronger than a magnitude 4. Right? So the difference between 4 and 7 means a lot. Well, this Rio scale runs from 0 to 10, and it has two components. It looks at the probability or the likelihood that the detection is real, and then how significant the detection is. And it's if it appears to be a signal that's coming from within our solar system, it's a lot more significant than something that's extragalactic in terms of its potential impact on Earth. And for me, the most important number on that scale is 0, because this is a way that we can very quickly tell the media, tell the world that this is a hoax. Don't pay any attention to this. And so, yes, we're trying to find some way of telling the general public how significant, how credible claimed discovery actually is.
So why do we read a lot about or hear about the post-detection disclosure protocol, or people having this opinion that if it ever happens that there is a disclosure that needs to be made, it would either be held back because of undetermined implications for society, or particularly for world religions, or the social fabric of everything would change? Is there something that you think would be the case? And should there be a protocol and decision made when and how to release this information?
Yes, I think there does need to be a protocol. I think you always do need to plan for success. And the protocol that you're talking about was first developed in the 1980s, and a collaboration between the International Academy of Astronautics and the International Institute of Space Law. And it said, it just said, look, do this the way you do any other science. You make sure that what you're about to announce isn't a fluke, it isn't an accident, it isn't noise. Verified, get a second independent confirmation of the signal, and then tell the world. But after that, the next line in the protocol says, and that there should be no transmission from Earth in response to this signal until there is a consensus globally about who will speak for Earth and what should they say. And we had no ability then or even now to give a good description of how that consensus could be reached. But it is still philosophically the high road, that's what we'd like to do. And of course, there's no enforceability whatsoever with this protocol. It's a bunch of scientists that say, yes, we think that this is the right way to go. There are precedents for this in biology, for scientists deciding that they would follow a certain group of rules. I honestly don't know. I think if we announce the detection of a signal tomorrow, everyone with access to a transmitter would in fact use that transmitter to say whatever the heck they wanted to say. Right?
Sing a song in space.
Right. And then Freeman Dyson chuckled when we say this, and he said, well, don't you think that cacophony would be the best description of Earth today that you could possibly make?
Yeah, absolutely. And I think also people get worried because if somebody has traveled all that distance to come here, they are going to be technically, obviously, very advanced. But do you feel that they don't necessarily have to have bad intentions? They may not attack us because we may be aggressive beings and we've cooled down a lot now. But that doesn't necessarily have to be their approach as well. What do you think about that?
Well, I actually very much agree with you. If they are a very advanced technology so that they can get here, then they are older than we are. And it seems to me that you can't become a long-lived, sustained technological civilization unless you've managed to suppress the aggressive parts of your behavior that probably helped you to get intelligent in the first place. But once you begin a cultural evolution, are in fact detriment. I think that it's very much the Steven Pinker idea that we are kinder and gentler than we have ever been, and cultural evolution will continue to drive us in that direction. So I'm not of the opinion that we would have anything to worry about, but there's no way of knowing until it happens.
Right. Also considering that universally, if there is a universal law, it is rather nurturing, and evolution on our planet could have led us to aggression because of resources or limited resources, but that doesn't mean that everybody is going to go through that same struggle for food and water and hunter-gatherer life. So it could be another planet where there's abundance, there's happiness, joy, and intellect comes there. So they don't see that part of it at all. They may not have aggression in their genes.
Well, yes. And again, we have only one example of evolution on this planet. But I think that aggression was part of as part of the predator-prey relationship is something that helped ratchet up intelligence on this planet. And so perhaps competition of some variety will be part of the evolution of intelligence elsewhere.
Right.
But at some point it becomes counterproductive. And you have to outgrow it if you're going to stay around.
Yeah. Angela, we would love to know a little bit more about Contact and the Carl Sagan book, followed by, of course, the movie. We've all seen the movie, and for a lot of us who are space enthusiasts, we've seen it more than 3 or 4 times. And I was watching it maybe a month ago again. I just wanted to know from you, what was your reaction when where did you see the movie for the first time? Did you go to a cinema, and what did you go through when you were watching the movie?
Well, I started with Contact when Carl sent me a pre-publication copy of the book, because he was a colleague. He and I had a lot of discussions about doing science as a woman, and I eventually decided that the main character in Contact is really Carl, right? And he had a number of female colleagues that he worked with and could put with his wife Anne, could put the female point of view on it. But I have to tell you, Carl died in December, and Contact the movie premiered in the spring. And we went to the premiere, walked the red carpet and all that good stuff. And in the closing scene, the closing credits, the last thing it says is, for Carl, which just started the tears, right? Because we had lost him. But it's a great movie that has a huge innumeracy, right? There is just some miserable math there. When there was a memorial service for Carl at JPL, the movie was still being edited and cut. But Ann Druyan, his widow, wanted to show a clip from the movie as part of that memorial service, because Carl had been working on it at the time of his death. And so, unfortunately, the clip that Warner Brothers gave her to show was this innumeracy, because it preceded the first kiss in the movie, and so it was the romantic anchor, and they knew that whatever else they cut, they weren't going to cut this. So you have this scene where Jodie Foster and Matthew McConaughey are sitting there at Arecibo looking up at the sky, and she says, look at all of those stars, 100 billion, right? And if only 1 in a million of those stars had planets, and if only 1 in a million of those planets had life, and if only 1 in a million of those life forms had transmitters, there would be millions of signals to find. So what's the math? It's 10 to the 11 multiplied by 10 to the minus 18, and that sure as heck isn't equal to 10 to the 6th. So, I mean, there's 13 orders of magnitude or so wrong in that equation. So as soon as we got out of the premiere and we went to this party afterwards down in Hollywood, I went and I got Jodie and the producer, and I said, you've got to change this. The math is just wrong. And I went and got the screenwriter. The young kid came over and he said, oh, I worked so hard on that. He said, I was sure I got it right. And going, dude, all you had to do was ask, right? You got to help you. And it, unfortunately, cinematically, it's just too close up on her face when she's saying this. So you can't change 1 in a million to 1 in 1,000, which would have made it a bit more correct. So it's there every time I see the film, and when on the 20th anniversary of that picture, I think I probably saw it a dozen times in that year. It just really gets me unhappy every time.
And a lot of us now, I said, after you just told that to us.
Oh, okay. Now you won't be able to unsee that, right?
Yeah. I mean, I thinking of it, I've watched it that many times, and I'm sure everybody listening is going to go back and go to that again. Yeah.
Well, actually, the thing that the producer said to me that made me so angry was, he said, "Oh, Dr. Tarter, how many people do you think are going to get that?" And to me, it's just a condemnation of the way that we teach our young people about math and how to think about large numbers and think about orders of magnitude and get it. We don't do a very good job at that.
Right. And do you think, Jill, that whenever this contact, or whenever we do come in touch with some kind of extraterrestrial, the reaction that would happen, would it be initial? Do you think it will cool down? Because in the last few years, if you're looking at the kind of television that I grew up on, or the kind of film that we've watched, there would be one science fiction sci-fi movie, let's say, and generally there were other movies, or you would have to get a comic book and things like that. But today, every channel or every network or everything on Netflix, every second or every third one is science fiction, and there is an alien, or there is it's a space movie, or there is a war between planets, the Star Wars. So I'm thinking about my son, and the way and I've had this conversation with him, and he seems to be so relaxed about it, because if it does happen, it happens. This generation I'm talking about would take it that way. So are we more receptive now than we were if this event would have happened?
Well, certainly we're more steeped in that storyline than we used to be. Right? This was so far out on the fringe when we first started trying to search for signals. And today it's just the next question that you ask once you know that all stars have planets, and some of those planets are like the Earth, and then the next thing you ask is, well, is there any life? So it is far more mainstream than it once was. And again, it's exoplanets and extremophiles that led to that difference. It's impossible to, I think, predict human behavior. I mean, humans in my country have behaved so abysmally in the last 10 days that which I never would have predicted. I just really don't know. We've actually held, it's NASA, so we held workshops on this question. How will people react? And we brought in religious leaders and psychologists and social scientists and media folks, and at the end of the day, they said, well, humans will react to this news in accordance with whatever cultural norms are there at the time. And you look at them and you said, we paid your airfare to give us that advice? No, it's really hard. I don't know how people will react. I think, as you pointed out, your son would not be as surprised as you might have been at his age, because he's just swimming in it. It's all around. It's part of the ethos now.
And before we let you go, Jill, if you had to speak to, or you are speaking, but if you had a message for all our listeners, and I think you would know that majority of our listeners are between the age group of 13 to 26 and 27. A lot of them are in college getting ready for education and university and fields that they want to get into. Would you have a message for them, both for the future, one, ethically in whatever field they do, collectively as a race, what they need to be looking out for, and then individually, careers that they wanted to choose and how should they choose those? How would you speak to them directly?
Well, I would like all of your listeners who have electronic devices to go in and change their profiles on each of those devices, so that the first thing they say about themselves is not that they're an American or an Indian or a European, but that they're an Earthling. Because I think this cosmic perspective is something that is incredibly important for our long-term future. We have so many challenges on this planet that don't respect national boundaries and are going to have to be worked on and solutions found globally. And so I think if they put themselves in that frame of reference, that they're an Earthling, I think that will go a long way to finding solutions to these challenges that we face. And in terms of what jobs and what careers, I would simply tell them, whatever it is you love, whatever it is that you really like to do, go to whatever kind of training and schooling that you need to become the best that you can possibly do at that thing. And then use the skills that you develop and your passion to look for problems that your skills can be useful in solving. And it may not be anything that you ever thought about. And probably the younger generation that we're talking to is not going to have one job the way I have. Right? from a career, they're probably going to do 2 or 3 or 4 different occupations or fields of interest, because when they start out, what they will end up doing won't exist. We're developing new technologies, new areas of scientific exploration that develop very rapidly. And so you need to get good skills, become a good problem solver in ways that you find appealing, and then go look for interesting problems to solve, and don't expect that it's going to be the same problem throughout your career.
True, very true. And again, before we let you go, Jill, we want to wish you a belated happy birthday. We are 2 or 3 days late. We should have started with a little birthday song, but that's from all of us here at the podcast. It's been an absolute pleasure talking to you.
I've enjoyed
a long time to do this. I'm still going to get over this, and as soon as you switch off now, I'm going to be listening to it again right now, right here. I just hope you've had a good time, Jill.
Thank you very much. I'll say goodbye.
इस हब हॉपर ओरिजिनल को सुनने के लिए आपका शुक्रिया। अगर आप भी अपना पॉडकास्ट लॉन्च करना चाहते हैं, तो हब हॉपर स्टूडियो वेबसाइट पे रजिस्टर करें और 1 मिनट के अंदर अंदर अपना खुद का पॉडकास्ट लॉन्च करें। यही नहीं, स्टूडियो देता है आपको पूरी आजादी कहीं भी कभी भी अपना पॉडकास्ट लॉन्च करने की, सिर्फ 3 आसान स्टेप्स में। तो साथ में अपना पॉडकास्ट शुरू करने के लिए तैयार? जस्ट हॉप ऑन हब हॉपर, सिंपली कंटेंट।